if you have a current source in parallel with a resistance, what comment can you make? You can think of it as it's voltage source in series with a resistor. What is the value of the voltage source? Think carefully, people. It is plus or minus? Minus Iref into Rx. So, that is Rx, and this voltage is minus Iref times Rx. All right. And what is the sanity check? You know, as Rx tends to infinity, what happens? Well, the impedance seen will go to infinity obviously, but the voltage is also going to infinity, so that the current is maintained at that Iref, pulling out of the source, correct? Okay. So, so of course, we can't get Rx is infinity, we will get Rx is in reality we will say Rx is large, right. So, what have we therefore done? We have replaced a current source with a large resistor and a large negative voltage source, correct. Okay. Now, so I mean now we have avoided the use of a current source, right, and concluded that if that Rx is made sufficiently large, that combination of Rx and the negative voltage source are indistinguishable from a current, and therefore, it shouldn't, I mean it should, for all practical purposes, the the stability of bias that the current source would give would also be given by this resistor, correct. All right. Now, unfortunately, there is a small problem. And what is the problem now? Earlier, how many supply voltages, how many voltage sources did you have? One. Now you have two, but the problem is there is basically a negative supply, right? Okay. So, if you want to avoid the negative supply, what do you think you can do? What do you think we can do? This is very similar to what you do with competitive exams, right? There is negative marking, correct? Okay. And it is very likely that a whole lot of candidates will get negative marks, correct? But then if it comes out to the press that people getting 0 are qualifying and studying in a top class institution, then it will become a huge PR nightmare. So, what will you do? You add 50 marks to everybody, right. So, the guy who is getting minus 30 basically feels happy that he has at least got 20, right, and the guy who has got 0 now all of a sudden has got 50, and then you tell everybody the minimum pass mark is 50, all right. I mean, it does not affect anything, right. Same thing in a network. What is the notion of if you add, so basically the what is the most negative potential in this network now? Minus Iref times Rx, okay. You do not want that. So, what will you do? I mean, typically you are used to the lowest potential being 0, correct. And so, what will you, so now what will you do? You are used to the most negative potential being 0. Unfortunately, it is not 0, it is minus Iref times Rx. So, what will you do? You add Iref times Rx to all node potentials, correct. And what effect will that have on the branch currents and in the network? If I take all the nodes in a network and move all their potentials up by same amount, what will happen? I mean, it's like giving everybody in the country, 2 crores and say, in India, everybody is crorepati. You understand? That's not helping anybody. Correct? Okay. Because, flow of money only depends on differences. Correct? Like flow of current. Alright. So, if all the voltages have gone up or gone down by the same amount, basically the currents in the branches will not change. Correct? So, the question, so now if I add Iref times Rx to all nodes, what comment can you make about the lower end of that Rx? 0, very good. Okay. What comment can you make about the lower end of R1? What potential must it be at? What was 0? Remember our analogy, right? Your marks are 0. So, I will make this plus Iref times Rx. Okay. What should I do with VDD? VDD plus Iref times Rx. All right. Okay. So, and what comment can you make about this potential? What was it previously? It was VDD times R1 over R1 plus R2, and now because we have moved everything up by the same amount, this potential will automatically be Iref times Rx plus VDD times R1 by R1 plus R2. All right. So, now if you now look at this circuit, right, what do we see? Well, this whole notion of Iref does not make any sense at all anymore, right. We can call this guy, we can call it, instead of calling this VDD plus Iref times Rx, we can call this, say, VDD hat. Correct? All right. Okay. What comment can you make about this this voltage? We want that to be this character here. Okay. All right. So, can we get, is there something you can think of to get rid of having to have that Iref times Rx? What can we do? We have VDD hat here. We need to get, what is the purpose of that R1 and R2? It is to bias that voltage properly, right. So, there is no real need to, for the lower end of that resistor R1 to be at Iref times Rx. If we ground it, but we still want, let us say we ground this, and we still want the same potential here, what will we do? Well, it's very easy. So, basically instead of R1 and R2, basically you say, okay, I am going to call this R1 hat and R2 hat, where the, the hats are basically go and appropriately change the, the resistor, so that the voltage at the gate remains what we wanted it to be. Okay. So, now therefore, there is no need for any of this. This is some VDD hat, R1 hat, R2 hat, Rx, RL1, where the understanding is that compared to the earlier circuit with the current source, what comment can we make about VDD hat? VDD hat should be expected to be much larger than VDD, right. Okay. In the limit, VDD hat should be infinite to get the same level of insensitivity to changes in supply voltage and all that stuff, right. Remember, when we had a current source in the source, the bias current in the transistor was absolutely insensitive to for instance changes in the gate potential or changes in the threshold voltage or whatever, correct, because the current in the drain would always be the same. All right. All right. Now, that can only be achieved if Rx equals infinity, which is which then will mean that VDD hat will be infinite, correct? But of course, in reality, that VDD hat is going to be finite, all right, and so will because Rx has to be finite, correct? And therefore, actually, then the next step is to say, well, you know, let's dispense with this hats, where here now it's understood that VDD, R1 and R2 are chosen appropriately, so that the current flowing in the transistor, let's say you want a current IREF in the transistor. How will we go about choosing you know, Rx, R1, R2 and VDD? We want a current IREF in the transistor. What do we do? Let's say we've chosen Rx. How will we figure out what R1 and R2 must be for a given VDD? What is the source potential? That is Rx times IREF. What is the gate voltage? Okay, VDD times R1 by R1 plus R2, which must also be equal to, how is it related to the transistor? I mean, how will you find it? We need IREF times IREF in the drain. So, how will you choose R1 and R2 given VDD? So, what is the gate voltage? It is of course VDD times R1 by R1 plus R2, right? That must be equal to, yeah, that's basically nothing but the gate source voltage of the transistor plus IREF times Rx. Is this clear, right? So, that basically, and what is VGS of the transistor? What is the current flowing through the transistor? So, what is the gate source voltage? So, that's nothing but, so the gate source transistor voltage of the transistor is nothing but Vt plus square root of 2 IREF over mu n C ox W by, all right, plus, so that is VGS plus IREF Rx. So, IREF is known, Rx is known, the transistor properties are known, so VGS is known, VDD is known. So, we know from this you can go and find the ratio between R1 and R2, and as usual we will choose the parallel combination of R1 and R2 to be much larger than Rs, all right. So, now if you want this circuit to, I mean, so staring at this picture, how do we convince ourselves that Rx actually helps in stabilizing the bias current? So, remember, I mean, think about it this way, if IREF attempts to increase for some reason, right, what comment can you make about the source potential? It will increase, thereby reducing VGS, and therefore will act in a way as to reduce IREF. Does it make sense? All right. So, now the question is, so we know that if this so called scheme has to be effective, that Rx must be large, right. So, now the obvious question is how large. So, how do we figure that out? So, earlier remember we were keeping Vg fixed, this was VDD and we had put IREF in the source, okay. Now, we have some other Vg which we call Vg hat, all right. We have some Rx and this is going you know, to some large voltage VDD hat, okay. And let us say this is also drawing IREF, all right. So, how will we, if you are in the lab, how will you figure out if Rx is you know, what experiment can we do to understand if that Rx is large enough? Okay. Look at this guy here. How will we convince ourselves that this you know, IREF stabilizes the bias? If you are in the lab, what will you do? Vary what? You wiggle Vg and see how much ID changes, right. So, what will you measure? I mean, if you did that experiment for the circuit on the left, circuit A, what will you see? If I wiggle Vg by a small amount, so in other words, if I change it by delta V, what comment can you make about the current in the transistor in circuit A? It will not change. Is that clear or it's not clear? Understand? All right. So now, what should we do now? So now, how do you, based on this discussion, can you tell me what we should do? How will we figure out if a certain Rx qualifies as a large Rx? We changed Vg by a little bit and observed the change in ID, right? And when we say the current doesn't change, what it basically, it doesn't make sense to talk about the absolute change in current. It only makes sense to talk about a relative change in current, correct? All right. So now, what will you, what comment can you make about circuit B? How will we figure out whether Rx is large or not? Changed Vg by a small amount delta V and saw what happens to the current. Okay, right? And what did we find? Delta I was 0. Okay. So now for circuit B, what will we do? We will vary gate voltage by a small amount delta V and just look at the change in the current. All right. So this current will change by some amount delta I. All right. And all that we are interested in is that delta I. Okay. So how will we figure out what the change in current is due to a change in the gate voltage by a small amount delta V? You can, one way is to write out the equations and solve the quadratic and so on, but because that delta V is a small change in the gate voltage, we can linearize the circuit about the operating point, which we know already, and therefore, so in the small signal equivalent, what happens? What should we have at the gate? We should have delta V, very good. What do we have in the source? All right. What should we have for the drain? Ground, very good. And what should we have as the drain current? Delta. All right, and we replace the transistor by its incremental equivalent. So and what is the control source? Let us call that Vx. What is the control source? Gm delta V minus Vx. Okay, very good. So now help me figure out delta I. So what is the unknown that we are trying to find out? Vx. So how will we find Vx? Okay. So basically you write KCL at the node Vx. So basically Vx by Rx must be equal to Gm times delta V minus Vx. Okay. So what does this mean? What is Vx? What is known and what is unknown in that equation? By 1 plus Gm Rx. Correct? All right. So what is delta I therefore? You know Vx. What is delta I? Simply Vx by Rx. Okay, so that basically is nothing but delta V times Gm over 1 plus Gm Rx. All right. Okay, sanity check. Sanity check. One sanity check is to look for Rx equal to infinity, and then what happens? Delta I should be 0. Why does that make sense? Yeah, so basically if you look at the incremental equivalent of this guy here, that is equivalent to this circuit with Rx equal to circuit. The incremental equivalent of circuit A is the same as that of circuit B for Rx equal to how much? Infinity, correct? And we know that in circuit A, if you change the gate voltage, the drain current does not change, correct? So sanity check is that if you set Rx equal to infinity in the expression we have, we must get. Okay, can somebody think of another sanity check? Rx is infinity is one choice. What is the other easy thing to check? One sanity check is, as all of you suggested, Rx is infinity, right? What is the other sanity check that you can do? Rx equal to 0. Okay, if you put Rx equal to 0, what delta I do you get? The math is telling us it is Gm delta V. Does that make sense or no? Yes, no? Yes. Why? Well, if Rx equal to 0, then it's a common source amplifier, right? Okay, if I wiggle the gate by a delta V, the current will change by Gm delta V, right? The process of adding that resistor Rx in the source is reducing the change in current from what would have originally been Gm times delta V by a large factor, right, or by a factor 1 plus Gm Rx, correct? All right. So now based on this discussion, can you tell me what it means to have a large Rx? What does it mean to have a large Rx? What constitutes a large Rx? Without Rx, the change would have been Gm delta V. What is the job of Rx? To reduce that change, right? I am telling you, or the equation is telling you that if I plop in an Rx, the change in current is going to be Gm delta V, which is the change without Rx, divided by this factor 1 plus Gm Rx. This is valid for all values of resistance Rx. So now the question I am asking you is, what constitutes a large Rx? So basically that number Gm Rx, so this change in the current will be very small if Gm Rx is much larger than 1, which is equivalent to saying that Rx must be much larger than 1 over Gm. All right, and okay, let me just finish this in a couple of minutes. So what is Gm in terms of the bias current? What is Gm? That's 2 Iref upon Vgs minus Vt. That must be much smaller than Rx. So which is equivalent to saying that Iref times Rx is much greater than Vgs minus Vt by 2, right. So saying Gm Rx is much larger than 1 is equivalent to saying that the voltage drop across that resistance Rx must be much larger than Vgs minus Vt by 2. Okay, the larger the better.